magnetic radiation with a wavelength of 608 nanometers. Now, what this looks like is, so we have the wavelength, and in a previous problem we've shown how you can take energy, or you can take wavelength and turn it into energy. And the equation was that energy equals Planck's constant times speed of light, which is c, 6.626, times 10 to the minus 34th. That's Planck's constant, and the units are going to be in joule seconds. Then the speed of light, c, is 3.00 times 10 to the 8th meters per second. And the wavelength is 608. That's nanometers, but we can replace nanometers by, so 1 nanometer equals 1 times 10 to the minus 9th meters. And therefore, instead of nanometers, I will write times 10 to the minus 9th meters. And then we can multiply this out to at least get the energy. Let's see, there we go. 6.626 exponent 34 minus times 3 exponent 8 divided by 608 exponent 9 minus. Yep, I can see that minus in there. And I get 3.27 times 10 to the minus 19 joules. And yeah, there we go. Rounding up to 3.27. Now it's time to talk about what this is. So this is the joules, or the energy associated with a single photon It is the energy associated with a single photon of light. And I could also say with a single photon of electromagnetic radiation, because a light, or visible light, is a type of electromagnetic radiation, with a single photon of light. So when we have see if I can, there we go. It's a little crooked there, but when we have one photon with a wavelength of 608 nanometers, it has this much energy. And so what I'm going to do is I'm going to put on the unit per photon here, or divided by photons, because this is the joules per one photon. And I know that does not come through in the equation, but it is a set of units that we can use. And it is important because we're going to turn this into kilojoules per mole and per mole of photons. So sorry, just checking the chat real quick there. So now what I'm going to do is I'm going to take this number of joules per photon, and you can write one photon there if you want. The one is understood if you don't. But now I'm going to convert joules into kilojoules by knowing that 1,000 joules equals 1 kilojoule. And I'm going for kilojoules per mole And the per mole is going to be per mole of photons. So 1 mole photons. And here's where it's, we retouch base with Avogadro's number. So 1 mole of anything, including photons, including atoms, including ions, is 6.022 times 10 to the 23rd photons, or whatever it is. But 1 mole of anything equals 6.022 times 10 to the 23rd of that thing. So that's how we're going to get, well, if we look at our photons cancels, our joules cancel, and we will be left with units of kilojoules per mole of photons, it turns out. And then we multiply this out. When we do, we get 3.27 exponent 19 minus divided by 1000 times 6.022 exponent 23rd, which is 196.9, or to 3 sig figs, 197 kilojoules per mole. And you can just go back to the kilojoules per mole part here. You don't have to write per mole of photons. We've always just written per mole before. And this 197 is the answer that you'll put in for the number for this part. Any questions?
Prof, what number is this? Is it number 10?
This is number 11.
11.
We did 10 before.